Welcome to Science Education channel. In this video we will discussing about foodborne diseases and food standards. 1. Food poisoning, food intoxication and food infection. 2. Clostridium, staphylococcal enterotoxic poisoning, and Bacillus cereus food poisoning, organism, source, foods involved, outbreak conditions, effect on human health and prevention. 3. Aflatoxin, sources of contamination, foods involved, effect on human health and prevention. 4. Introduction to FDA, BIS and FSSAI objectives and responsibilities. 5. Introduction to HACCP. Foodborne diseases and food standards. The diseases caused due to consumption of contaminated food is called as foodborne diseases. These are classified into two main categories. 1. Food poisoning. 2. Food infection. Food poisoning. Food poisoning are those diseases which are caused due to the consumption of toxins produced by contaminated microorganisms in the food. Depending upon the type of organism involved in food poisoning, 3 types of food poisoning are recognized. These are 1. Bacterial, 2. Fungal, 3. Algal. Most common bacterial food poisoning includes 1. Botulism, 2. Staphylococcal food poisoning. Botulism is a neuroparalytic disease caused by ingested food containing the neurotoxin produced by an anaerobic soil bacteria, i.e. Clostridium botulinum. It is a gram-positive, rod-shaped, spore-forming and anaerobic bacteria commonly present in the soil and animal fecal matter. Optimum growth temperature is 28 degrees Celsius and pH 7.2. There are 7 types of toxigenic species of C. botulinum designated as types A, B, C, D, A, F, G based upon their production of different 7 types of neurotoxins. Organism and sources of botulism. The spores of C. botulinum remains in the soil and animal dung, which contaminates the food and food products during processing and preservation methods. When the food preservation methods such as canning, pickling etc. are improper and storage conditions are inadequate, the contaminated spores of C7 botulinum germinates and forms vegetative cells which produce toxin in the food. The toxins persist in the food for fairly long period when food are stored at low temperature. High protein content of the food and room temperature favors the toxin production. Foods involved in the United States, inadequately processed home canned foods are most often the cause of botulism. In Europe the main causes are preserved meats and fish. Commercially processed foods have accounted for less than 10% of the outbreaks, while home-processed foods were responsible for 72% of the outbreaks. Home-canned foods like string beans, sweet corn, beets, asparagus, spinach, and chard are most often responsible for botulism. In general, the low and medium acid canned foods are most often incriminated, but there have been exceptional instances of poisoning from acid foods, such as tomatoes, apricots, pears, and peaches. These acid food had been grossly underprocessed, and the underprocessing had permitted the growth of other microorganisms to aid growth and toxin production by C. botulinum. Conditions necessary for an outbreak. The following conditions are necessary for an outbreak of botulism. 1. Presence of spores of C. botulinum of type A, B, or A in the food being canned or being processed in some other way, and produce. 2. A food in which the spores can germinate and the Clostridia can grow toxin. 3. Survival of the spore of organism. Egg, because of inadequate heating in canning or inadequate processing otherwise. 4. Environmental conditions after processing that will permit germination of the spores and growth and toxin production by the organism. 5. insufficient cooking of the food to inactivate the toxin. And 6. Ingestion of the toxin-bearing food. Pathogenesis and symptoms of botulism, the neurotoxin produced by Cl. Botulinum is proteinous in nature and highly toxic to man. A very minute dose, 0.01 mg, is sufficient to cause botulism. After ingestion, the neurotoxin is assimilated into the small intestine and damage involuntary nerve fibers, hence called neurotoxin, resulting into paralysis. The incubation period of botulism is about 12 to 36 hours. The symptoms of disease appear within 12 to 36 hours. After ingestion of contaminated food, the symptoms of botulism include abdominal pain, headache, nausea, vomiting, diarrhea and weakness. In the latter stage, there is constipation, double vision, difficulty in food, swallowing, paralysis of respiratory system which may lead to death. Death may occur within 3 to 6 days of infection if not treated. Diagnosis: botulism can be diagnosed 1. By isolation and detection of C. botulinum in the stool and vomiting of the patient and suspected food. 2. Demonstration of anti-neurotoxin antibodies in the patient serum by the serological test. Treatment: botulism can be treated by the administration of the botulinum antitoxin at the early stage of disease. Other treatment methods include artificial respiration, bed rest and maintenance of fluid balance of the body. Prevention: following precautions are to be taken to prevent botulism. 1. Canned food should be properly processed and stored. 2. Consumption of spoiled canned food should be avoided. 3. Reheating of canned food before eating if stored for long period. 4. Maintenance of good sanitary practices and aseptic conditions during preparation and handling of food to prevent contamination with Cl. botulinum. Staphylococcus food intoxication. One of the most commonly occurring food poisoning is caused by the ingestion of the enterotoxin formed in food during growth of certain strains of Staphylococcus aureus. The toxin is termed an enterotoxin because it causes gastroenteritis or inflammation of the lining of the intestinal tract. Organism and source: the organism is gram-positive and a typical Staphylococcus occurring in masses like clusters of grapes or in pairs and short chains. Growth on solid media usually is golden or yellow but may be impigmented in some strains. Most enterotoxin-producing S. aureus cultures are coagulase positive, coagulating blood plasma, produce a thermal stable nuclease, and are facultative in their oxygen requirements in a complex glucose medium but grow better aerobically than anaerobically. S. aureus produces 6 serologically distinct enterotoxins, A, B, C, D, and A, that differ in toxicity. Most food poisoning is from type A. The sources from which the food poisoning Staphylococci enter foods are for the most part human or animal. The nasal passages of many persons are laden with these organisms, which are a common cause of sinus infections. Also, boils and infected wounds may be sources. The human skin apparently is a source of these bacteria only when they have come from nasal passages or local infections. Staphylococci are becoming increasingly important in causing mastitis in cows, and some of these cocci can form enterotoxin in milk or milk products. The enterotoxin: the staphylococcal enterotoxins are simple proteins with molecular weights between 26,000 and 30,000. The single polypeptide chains are cross-linked by a disulfide bridge to form a characteristic cysteine loop. Since many of the amino acids in this loop are similar in catch of the enterotoxin types, it is thought to be the toxic part of the molecule. Of the several types of enterotoxins, A and D are more often associated with food poisoning outbreaks. Appreciable levels of enterotoxin are produced only after considerable growth of the Staphylococcus, usually a population of at least several millions per milliliter or gram must be attained. Therefore, the conditions that favor toxin production are those best for growth of the Staphylococcus. Toxin is produced at an appreciable rate at temperatures between 15.6 and 46.1 C. And production is best at 40 degrees Celsius. Under the best conditions, enterotoxin may become evident within 4 to 6 hours. The lower the temperature during growth, the longer it will take to produce enough enterotoxin to cause poisoning. Enterotoxin has been demonstrated in a good culture medium in 3 days at 18 degrees Celsius and in 12 hours at 37 degrees Celsius, but not in 3 days at 15 degrees Celsius, 7 days at 9 degrees Celsius, or 4 weeks at 4 to 6.7 degrees Celsius. Production of enterotoxin by the Staphylococci is more likely when competing microorganisms are absent, few, or inhibited for some reason. Therefore, a food that had been contaminated with the Staphylococci after a heat process would be favorable for toxin production. An important characteristic of the enterotoxins is their stability toward heat. Foods involved custard and cream-filled bakery goods, ham, and poultry have caused the most outbreaks of Staphylococcus food poisoning. About 75% of all staphylococcal food poisoning outbreaks occur because of inadequate cooling of foods. Other foods incriminated include other meats and meat products, fish and fish products, milk and milk products, cream sauces, salads, puddings, custards, pies, and salad dressings. The fillings in bakery goods usually are good culture media in which the Staphylococci can grow during the time that these foods are held at room temperatures. The disease individuals differ in their susceptibility to Staphylococcus poisoning. So that of a group of people eating food containing toxins, some may become very ill and a lucky few may be affected little or not at all. The incubation period, time between consumption of the food and appearance of the first symptoms, for this kind of poisoning usually is brief, 2 or 4 hours, ranging from 1 to 7 hours. Differing in this respect from the other common food poisonings and infections, which usually have longer incubation periods. The most common human symptoms are salivation, then nausea, vomiting, retching, abdominal cramping of varying severity, and diarrhea. Blood and mucus may be found in stools and vomitus. In severe cases, headache, muscular cramping, sweating, chills, prostration, weak pulse, shock, and shallow respiration may occur. Conditions necessary for an outbreak. The following conditions are necessary for an outbreak of Staphylococcus food poisoning. 1. The food must contain enterotoxin-producing Staphylococci. 2. The food must be a good culture medium for growth and toxin production by the Staphylococci. 3. The temperature must be favorable to growth of the cocci, and enough time mag be allowed for production of enterotoxin. And 4. The enterotoxin-bearing food must be ingested. Prevention. The means of prevention of outbreaks of Staphylococcus food poisoning include 1. Prevention of contamination of the food with the Staphylococci. 2. Prevention of the growth of the Staphylococci. And 3. Killing Staphylococci in foods. Contamination of foods can be reduced by general methods of sanitation. By using ingredients free from the cocci, egg, pasteurized rather than raw milk, and by keeping employees away from foods when these workers have staphylococcal infections in the form of colds, boils, carbuncles, etc. Growth of the cocci can be prevented by adequate refrigeration of foods in some instances, by adjustment to a more acid pH. Also, the addition of a bacteriostatic substance, such as serine or an antibiotic, has been suggested. Some foods may be pasteurized to kill the Staphylococcus before exposure of the foods to ordinary temperatures, e.g. pasteurization of custard-filled puffs and eclairs for 30 minutes at 190.6 to 218.3 degrees Celsius oven temperature. Food infection. The foodborne diseases caused due to the entry of pathogenic microorganisms in the body through the ingestion of contaminated food is called as food infection. The most common food infection is salmonellosis, typhoid and paratyphoid fever. Organism salmonellosis is a gastrointestinal disturbance, enteric fever, resulting from the consumption of food contaminated with the species of Salmonella typhi and Salmonella paratyphi. The species of Salmonella causes food infection in man. Salmonella species are gram-negative, rod shape, non-spore forming and facultative anaerobic bacteria. It is actively motile by Peritrichus flagella. Optimum growth temperature is 37 degrees Celsius and optimum pH 7.00. It multiplies rapidly in the food kept at room temperature. Sources of salmonellosis. The most common source of salmonellosis is the contaminated milk, fish, meat, eggs and their products. Sewage. Contaminated water, if used for washing food, may become the source of salmonellosis. Food involved. A large variety of foods are involved in causing outbreaks of salmonella infections. Most commonly incriminated are various kinds of meats, poultry and products from them, especially if they are held unrefrigerated for long periods. Fresh meats may carry salmonella bacteria that cause disease in the slaughtered animals or may be contaminated by handlers. Meat products, such as meat pies, hash, sausages, cured meats, ham, bacon, and tongue, sandwiches, and chili, often are allowed to stand at room temperatures, permitting the growth of salmonella. Milk and milk products, including fresh milk, fermented milks, ice cream, and cheese, have caused infections. Since eggs may carry the salmonella, foods made with eggs and not sufficiently cooked or pasteurized may carry live organisms, e.g., pastries filled with cream or custard, cream cakes, baked Alaska, and eggnog. Conditions necessary for an outbreak. The following conditions are necessary for an outbreak of a foodborne salmonella gastrointestinal infection. 1. The food must contain or become contaminated with the salmonella bacteria. 2. These bacteria must be there in considerable numbers, either because of contamination or more often because of growth. These high numbers mean that the food must be a good culture medium, the temperature must be favorable, and enough time must be allowed for appreciable growth, and 3. The viable organisms must be ingested. Pathogenesis and symptoms. The salmonella organisms ingested through the contaminated food attach to the mucosal and submucosal layer of the intestine and multiply. Then it enters into blood circulation and localize into the organs such as spleen, liver, lung, lymph node, bone marrow, where they multiply further very rapidly. Then again enter into the blood circulation and destroy blood cells, produce endotoxin and results into the appearance of clinical symptoms of the disease. Incubation period of typhoid fever is 10 to 20 days and that of paratyphoid fever is 5.14 days. Clinical symptoms of salmonellosis includes nausea, abdominal pain, diarrhea, headache, fluctuating fever with chill, muscular weakness, restlessness, drowsiness, watery greenish foul-smelling stool etc. In severe condition, ulcers are developed throughout the small intestine. If untreated, death may occur within 3 to 6 days. However, death rate is very low, i.e. less than 19%. Diagnosis. Salmonellosis can be diagnosed in the laboratory from the suspected food in the stool and urine sample collected from the patient by isolation and detection of Salmonella species. A serological test called as Widal test is very much useful for the diagnosis of salmonellosis from the patient's serum. Treatment 1. Administration of saline or oral rehydration therapy to overcome dehydration due to loss of water and salts in diarrhea. 2. Application of antibiotics like chloramphenicol, tetracycline, ciprofloxacin. 3. Administration of typhoid vaccine. Prevention and control measures. 1. Prevention of contamination of food by infected person. 2. Unhygienic food processing and aseptic handling of food. 3. Cleaning and washing of the food by properly purified water and proper disposal of sanitary sewage. 4. Thorough cooking of the meat, fish, poultry, eggs etc. 5. Proper refrigeration of cooked food during long storage. C. Perfringens food poisoning. C. Perfringens food poisoning is usually a mild clostridial infection. C. Perfringens is widely distributed in feces, soil, air, and water. Contaminated meat has caused many outbreaks. C. Perfringens spores sometimes survive cooking. They can germinate and multiply, resulting in large numbers of bacteria when cooked meat that is contaminated with C. perfringens is left at room temperature or even up to 60 degrees Celsius, 140 degrees Fahrenheit, as on a warming table, for a period of time. Outbreaks typically occur in commercial establishments and rarely at home. Once inside the gastrointestinal tract, C. perfringens produces an enterotoxin that acts on the small bowel. Only C. perfringens type A has been definitively linked to this food poisoning syndrome. Mild gastroenteritis is most common, with onset of symptoms 6 to 24 hours after ingestion of contaminated food. The most common symptoms are watery diarrhea and abdominal cramps. Vomiting and fever are unusual. Symptoms typically resolve within 24 hours. Severe or fatal cases rarely occur. Diagnosis of Clostridium perfringens food poisoning. Identification of organisms in food or stool or of enterotoxin in stool. Diagnosis of C. perfringens food poisoning is based on epidemiologic evidence and isolation of large numbers of organisms from contaminated food or from stools of affected people or on direct identification of enterotoxin in stool samples. Treatment of Clostridium perfringens food poisoning. Supportive care. Treatment of C. perfringens food poisoning is supportive. Antibiotics are not given. To prevent disease, people should promptly refrigerate leftover cooked meat and reheat it thoroughly, internal temperature, 75 C, before serving. Bacillus cereus food poisoning. Bacillus cereus gastroenteritis. Mainly two types of disease syndromes are caused by B. cereus. Diarrheal syndrome is due to the production of heat labile enterotoxins during growth of vegetative cells in the small intestine of the host, and the infective dose is 10 to 10 cells per gram of food. This syndrome is mild and primarily manifested by abdominal cramps and diarrhea following an incubation period of 8 to 16 h and lasting for 6 to 12 h. Diarrhea may be mild or profuse and watery. This type is referred to as the long incubation or diarrheal form of the disease, and it resembles food poisoning caused by Clostridium perfringens. Another form is the emetic syndrome, which is more severe and acute than diarrheal syndrome and is referred to as short incubation or emetic form of the disease. Emetic syndrome is characterized by nausea and vomiting and abdominal cramps. The toxin responsible for this syndrome is a small cyclic heat-stable peptide which causes vomiting after 1 to 6 h of ingestion, average 2 to 5 h. The toxin is preformed and indigested with food. In emetic type of illness, the dose is about 105 to 10 cells per gram in order to produce sufficient toxin. It resembles Staphylococcus aureus food poisoning in its symptoms and incubation period. The number of organisms necessary to cause this syndrome seems to be higher than that of the diarrheal syndrome. In either syndrome, the illness usually lasts less than 24 hours. In a few patients, symptoms may last longer. Both syndromes arise as a result of the fact that B. cereus spores can survive normal cooking procedures. Under improper storage conditions after cooking, the spores germinate and the vegetative cells multiply. Toxins are hemolysin. B. cereus produces one emetic toxin, 8A, and 3 different enterotoxins. 3 pore-forming enterotoxins, responsible for the diarrheal type of food poisoning BL, HBL. Non-hemolytic enterotoxin, NHE, and cytotoxin K, CYTK. HBL and NHE each consist of 3 different protein components, named L2, Li, and B, and NHEA, NHE-B and NHEC, respectively. While CYT is a single-component toxin. The emetic syndrome, due to 8A, is an intoxication that is caused by a single highly heat, proteolysis, acid and alkali-resistant toxin that is preformed when ingested, leading to rapid onset of the syndrome. The emetic toxin, 8A, is dodecadepsipeptide circulide and having a ring-shaped structure of 3 repeats of 4 amino acids with a molecular weight of 1.2 kilodaltons. The mechanism and site of action of this toxin is unknown, although the small molecule forms ion channels and holes in membranes. Aflatoxin. Food microbiology and milk microbiology. Aflatoxins are various poisonous carcinogens and mutagens that are produced by certain molds, particularly Aspergillus species. The fungi grow in soil, decaying vegetation and various staple foodstuffs and commodities such as hay, sweet corn, wheat, millet, sorghum, cassava, rice, chili peppers, cottonseed, peanuts, tree nuts, sesame seeds, sunflower seeds, and various spices. In short, the relevant fungi grow on almost any crop or food. When such contaminated food is processed or consumed, the aflatoxins enter the general food supply. They have been found in both pet and human foods, as well as in feedstocks for agricultural animals. Animals fed contaminated food can pass aflatoxin transformation products into eggs, milk products, and meat. For example, contaminated poultry feed is the suspected source of aflatoxin-contaminated chicken meat and eggs in Pakistan. Children are particularly affected by aflatoxin exposure, which is associated with stunted growth, delayed development, liver damage, and liver cancer. An association between childhood stunting and aflatoxin exposure has been reported in some studies but could not be detected in all. Furthermore, a causal relationship between childhood stunting and aflatoxin exposure has yet to be conclusively shown by epidemiological studies. Though such investigations are underway, adults have a higher tolerance to exposure, but are also at risk. No animal species is immune. Aflatoxins are among the most carcinogenic substances known. After entering the body, aflatoxins may be metabolized by the liver to a reactive epoxide intermediate or hydroxylated to become the less harmful aflatoxin M. Aflatoxin poisoning most commonly results from ingestion. But the most toxic aflatoxin compound, B, can permeate through the skin. The United States Food and Drug Administration, FDA, action levels for aflatoxin present in food or feed is 20 to 300 ppb. The FDA has had occasion to declare both human and pet food recalls as a precautionary measure to prevent exposure. The term, aflatoxin, is derived from the name of the species Aspergillus flavus, in which some of the compounds first were discovered. The word was coined around 1960 after its discovery as the source of turkey X disease. Aflatoxins form one of the major groupings of mycotoxins. And apart from Aspergillus flavus, various members of the group of compounds occur in species such as Aspergillus parasiticus, Aspergillus pseudocaulatus, Aspergillus pseudomonas, and Aspergillus nomeus. Major types and their metabolites. Aflatoxin B is considered the most toxic and is produced by both Aspergillus flavus and Aspergillus parasiticus. Aflatoxin M is present in the fermentation broth of Aspergillus parasiticus, but it and aflatoxin Mi are also produced when an infected liver metabolizes aflatoxin B, and by aflatoxin B and B, AFB. Produced by Aspergillus flavus and 4-parasitica aflatoxin G, and G, AFG. Produced by some group 2 of flavus and Aspergillus parasiticus. 17 Aflatoxin M, AFM, metabolite of aflatoxin B. In humans and animals, exposure in Ng levels may come from a mother's milk, aflatoxin Mi, metabolite of aflatoxin B, in milk of cattle fed on contaminated aflatoxacol, AFL. Metabolite produced by breaking down the lactone ring foods. Aflatoxin Q, AFQ, major metabolite of AFB, in vitro liver preparations of other higher vertebrates. AFM, AFQ, and AFL retain the possibility to become an epoxide. Nevertheless, they appear much less capable of causing mutagenesis than the unmetabolized toxin. Contamination conditions. Aflatoxins are produced by both Aspergillus flavus and Aspergillus parasiticus, which are common forms of weedy molds widespread in nature. The presence of those molds does not always indicate that harmful levels of aflatoxin are present, but does indicate a significant risk. The molds can colonize and contaminate food before harvest or during storage, especially following prolonged exposure to a high humidity environment, or to stressful conditions such as drought. The native habitat of Aspergillus is in soil, decaying vegetation, hay, and grains undergoing microbiological deterioration. But it invades all types of organic substrates whenever conditions are favorable for its growth. Favorable conditions for production of aflatoxins include high moisture content, at least 7%, and temperatures from 55 degrees Fahrenheit, 13 degrees Celsius, to 104 degrees Fahrenheit, 40 degrees Celsius, optimum 27 to 30 degrees Celsius, 81 to 86 degrees Fahrenheit. Aflatoxins have been isolated from all major cereal crops, and from sources as diverse as peanut butter and cannabis. The staple commodities regularly contaminated with aflatoxins include cassava, chilies, corn, cottonseed, millet, peanuts, rice, sorghum, sunflower seeds, tree nuts, wheat, and a variety of spices intended for human or animal consumption. Aflatoxin transformation products are sometimes found in eggs, milk products, and meat when animals are fed contaminated grains. Organic crops, which are not treated with fungicides, may be more susceptible to contamination with aflatoxins. Prevention. There is very limited evidence to show that agricultural and nutritional education can reduce exposure to aflatoxin in low to middle income countries. Pathology. No animal species is known to be immune to the acute toxic effects of aflatoxins. Adult humans have a high tolerance for aflatoxin exposure and rarely succumb to acute aflatoxicosis. But children are particularly affected, and their exposure can lead to stunted growth and delayed development, in addition to all the symptoms mentioned below. High-level aflatoxin exposure produces an acute hepatic necrosis, acute aflatoxicosis, resulting later in cirrhosis or carcinoma of the liver. Acute liver failure is made manifest by bleeding, edema, alteration in digestion, changes to the absorption and/or metabolism of nutrients, and mental changes and/or coma. Chronic subclinical exposure does not lead to symptoms so dramatic as acute aflatoxicosis. Chronic exposure increases the risk of developing liver and gallbladder cancer. As aflatoxin metabolites may intercalate into DNA and alkylate the bases through epoxide moiety, this is thought to cause mutations in the p53 gene, an important gene in preventing cell cycle progression when there are DNA mutations, or signaling apoptosis, programmed cell death. These mutations seem to affect some base pair locations more than others. For example, the third base of codon 249 of the p53 gene appears to be more susceptible to aflatoxin-mediated mutations than nearby bases. As with other DNA alkylating agents, aflatoxin B can cause immune suppression, and exposure to it is associated with an increased viral load in HIV-positive individuals. The expression of aflatoxin-related diseases is influenced by factors such as species, age, nutrition, sex, and the possibility of concurrent exposure to other toxins. The main target organ in mammals is the liver, so aflatoxicosis primarily is a hepatic disease. Conditions increasing the likelihood of aflatoxicosis in humans include limited availability of food, environmental conditions that favor mold growth on foodstuffs, and lack of regulatory systems for aflatoxin monitoring and control. A regular diet including herbaceous vegetables, such as carrots, parsnips, celery, and parsley may reduce the carcinogenic effects of aflatoxin. There is no specific antidote for aflatoxicosis. Symptomatic and supportive care tailored to the severity of the liver disease may include intravenous fluids with dextrose, active vitamin K, B vitamins, and a restricted but high-quality protein diet with adequate carbohydrate content. In other animals, in dogs, aflatoxin has potential to lead to liver disease. Low levels of aflatoxin exposure require continuous consumption for several weeks to months in order for signs of liver dysfunction to appear. Some articles have suggested the toxic level in dog food is 100 to 300 ppb and requires continuous exposure or consumption for a few weeks to months to develop aflatoxicosis. No information is available to suggest that recovered dogs will later succumb to an aflatoxin-induced disease. Turkeys are extremely susceptible to aflatoxicosis. Recent studies have revealed that this is due to the efficient cytochrome P450-mediated metabolism of aflatoxin B in the liver of turkeys and deficient glutathione S transferase-mediated detoxification. Some studies on pregnant hamsters showed a significant relationship between exposure of aflatoxin B, 4 mg per kilogram, single dose, and the appearance of developmental anomalies in their offspring. Detection in humans. There are two principal techniques that have been used most often to detect levels of aflatoxin in humans. The first method is measuring the AFB guanine adduct in the urine of subjects. The presence of this breakdown product indicates exposure to aflatoxin B during the past 24 hours. This technique measures only recent exposure. However, due to the half-life of this metabolite, the level of AFB guanine measured may vary from day to day, based on diet. It is not ideal for assessing long-term exposure. Another technique that has been used is a measurement of the AFB, albumin adduct level in the blood serum. This approach provides a more integrated measure of exposure over several weeks or months. Food safety. The objectives of the control, regulation and inspection of food safety are primarily to give assurance that foods received by the consumer will be pure, healthful and of the quality claimed. Enforcement and control agencies for food safety range from international and private, briefly illustrated below. Food and Drug Administration, FDA. Introduction to FDA. The U.S. Food and Drug Administration, FDA, is composed of 7 centers responsible for ensuring the safety, efficacy, oversight and security of the nation's human and veterinary drugs, tobacco products, biological products, medical devices, food, cosmetics and products that emit radiation. The Food and Drug Administration, FDA, is an agency within the U.S. Department of Health and Human Services. It consists of the Office of the Commissioner and 4 directorates overseeing the core functions of the agency: medical products and tobacco, foods and veterinary medicine, global regulatory operations and policy, and operations. Objectives and responsibility of FDA. Protecting the public health by assuring that foods, except for meat from livestock, poultry and some egg products which are regulated by the U.S. Department of Agriculture, are safe, wholesome, sanitary and properly labeled, ensuring that human and veterinary drugs and vaccines and other biological products and medical devices intended for human use are safe and effective, protecting the public from electronic product radiation, assuring cosmetics and dietary supplements are safe, and regulating tobacco products properly labeled, advancing the public health by helping to speed product innovations. FDA's responsibilities extend to the 50 United States, the District of Columbia, Puerto Rico, Guam, the Virgin Islands, American Samoa, and other U.S. territories and possessions. The scope of FDA's regulatory authority is very broad. FDA's responsibilities are closely related to those of several other government agencies. Often frustrating and confusing for consumers is determining the appropriate regulatory agency to contact. The following is a list of traditionally recognized product categories that fall under FDA's regulatory jurisdiction. However, this is not an exhaustive list. In general, FDA regulates foods, including dietary supplements, bottled water, food additives, infant formulas, other food products, although the U.S. Department of Agriculture plays a lead role in regulating aspects of some meat, poultry, and egg products. Drugs, including prescription drugs, both brand name and generic, non-prescription, over-the-counter drugs. Biologics, including vaccines for humans, blood and blood products, cellular and gene therapy products, tissue and tissue products, allergenics, medical devices, including simple items like tongue depressors and bedpans, complex technologies such as heart pacemakers, dental devices, surgical implants and prosthetics, electronic products that give off radiation, including microwave ovens, X-ray equipment, laser products, ultrasonic therapy equipment, mercury vapor lamps, sun lamps, cosmetics, including color additives found in makeup and other personal care products, skin moisturizers and cleansers, nail polish and perfume, veterinary products, including livestock feeds, pet foods, veterinary drugs and devices, tobacco products, including cigarette tobacco, roll your own tobacco, smokeless tobacco. Bureau of Indian Standards, BIS, and Laboratory Recognition Scheme, LRS. Introduction. The Bureau of Indian Standards, BIS, the national standards body of India responsible for formulating Indian standards, was established under the Bureau of Indian Standards Act, 1986. To protect the interest of consumers, BIS operates a product certification scheme. Under the scheme, BIS grants licenses to such manufacturers who are capable of producing goods on continuous basis as per relevant Indian standards. Testing being necessary adjunct to product quality evaluation, the need for making available required testing facilities arises. It is in this context that BIS has established a network of 8 laboratories of its own in the country to cater to testing of samples generated from its product certification scheme. The Laboratory Recognition Scheme is governed by the provisions under Section 10(1)(h) of the BIS Act 1986 and the BIS Rules, 1987, 10(2)(a) and (b). These statutory provisions confer upon BIS powers to recognize any laboratory in India or in any other country for carrying out testing of samples in relation to use of the standard mark and such other functions as may be necessary. The rules also provide for the recognition of a recognized laboratory by the Bureau for non-fulfillment of any condition laid down at the time of recognition. The guidelines for recognition and the recognition of the laboratories have been laid down by the Bureau in this scheme. BIS also maintains a register of such laboratories as are recognized by it for testing of samples of articles or processes in relation to relevant Indian standards. The competent authority for operation of the scheme is SC.G. in Chief, Laboratories. Objectives and responsibilities of BIS LRS. It is neither physically possible nor economically viable for BIS laboratories to develop testing facilities for each and every product covered under BIS Product Certification Scheme. Accordingly, this Laboratory Recognition Scheme, LRS, has been formulated with the objective of having a sufficient number of outside laboratories in India and abroad, in addition to BIS labs, to cater to the needs of Product Certification Scheme. Scope of BIS LRS 1. This scheme lays down the criteria, terms and conditions of recognition, renewal, suspension. The recognition, appeal, complaint handling mechanism, administrative instructions for testing and issuing test reports and charges relating to recognition of outside labs. 2. The recognition shall in no way be a guarantee from BIS concerning utilization of lab for testing of samples drawn under BIS Product Certification Scheme. Food Safety and Standards Authority of India, FSSAI. Introduction. Food Safety and Standards Authority of India, FSSAI, is a statutory body established under the Ministry of Health and Family Welfare, Government of India. The FSSAI has been established under the Food Safety and Standards Act, 2006, which is a consolidating statute related to food safety and regulation in India. FSSAI is responsible for protecting and promoting public health through the regulation and supervision of food safety. The FSSAI is headed by a non-executive chairperson, appointed by the central government, either holding or has held the position of not below the rank of Secretary to the Government of India. Rajesh Bhushan is the current chairperson for FSSAI and Shri Arun Singhal is the current Chief Executive Officer for FSSAI. The FSSAI has its headquarters at New Delhi. The authority also has 6 regional offices located in Delhi, Guwahati, Mumbai, Kolkata, Kochi, and Chennai. 14 referral laboratories notified by FSSAI. 72 state, UT laboratories located throughout India and 112 laboratories, NABL accredited private laboratories, notified by FSSAI in 2021. With the aim of benefiting industries involved in manufacturing, handling, packaging and selling of food items, FSSAI decided to grant perpetual licenses to restaurants and food manufacturers on the condition that they file their returns every year. FSSAI was established by former Union Minister Dr. Ambumani Ramadoss, Government of India on 5 August 2011 under Food Safety and Standards Act, 2006, which was operationalized in year 2006. The FSSAI consists of a chairperson and 22 members. The FSSAI is responsible for setting standards for food so that there is one body to deal with and no confusion in the minds of consumers, traders, manufacturers, and investors. Ministry of Health and Family Welfare, Government of India is the administrative ministry of Food Safety and Standards Authority of India. The following are the statutory powers that the FSS Act, 2006 gives to the Food Safety and Standards Authority of India, FSSAI. 1. Framing of regulations to lay down food safety standards. 2. Laying down guidelines for accreditation of laboratories for food testing. 3. Providing scientific advice and technical support to the central government. 4. Contributing to the development of international technical standards in food. 5. Collecting and collating data regarding food consumption, contamination, emerging risks, etc. 6. Disseminating information and promoting awareness about food safety and nutrition in India. Objectives and responsibilities. The Food Safety and Standards Authority of India is a statutory body under Food Safety and Standards Act, 2006. The Food Safety and Standards Act, FSS, 2006 is the primary law for the regulation of food products. This act also sets up the formulation and enforcement of food safety standards in India. The FSSAI appoints food safety authorities on the state level. The FSSAI functions under the administrative control of the Ministry of Health and Family Welfare. The main aim of FSSAI is to 1. Lay down science-based standards for articles on food. 2. To regulate the manufacture, storage, distribution, import, and sale of food. 3. To facilitate the safety of food. The FSS Act is a bucket for all the older laws, rules and regulations for food safety. The FSS Act took 7 older acts into one umbrella. 1. Prevention of Food Adulteration Act, 1954. 2. Fruit Products Order, 1955. 3. Meat Food Products Order, 1973. 4. Vegetable Oil Products Control Order, 1947. 5. Edible Oils Packaging Regulation Order, 1988. 6. Solvent Extracted Oil, Do-Oiled Meal and Edible Flour Control Order, 1967. 7. Milk and Milk Products Order, 1992. Departments. 1. Science and Standards Division, I&LE. 2. Regulations Division. 3. Quality Assurance Division, 1 and LE. 4. Regulatory Compliance Division. 5. Human Resource and Finance Division. 6. General Administration and Policy Coordination Division. 7. Information Technology Division. 8. Social and Behavioral Change Division. 9. Trade and International Cooperation Division. 10. Training Division. 11. Rajbhasha. Microbiological criteria for food safety. The stated chief purposes of microbiological criteria for foods are to give assurance, 1. That the foods will be acceptable from the public health standpoint, i.e., will not be responsible for the spread of infectious disease or for food poisoning. 2. That the foods will be of satisfactory quality, i.e., will consist of good original materials that have not deteriorated or become unduly contaminated during processing, packaging, storage, handling, or marketing. 3. That the foods will be acceptable from an aesthetic viewpoint in that the introduction of filth in the form of fecal material, parts of vermin, pus cells, mold mycelium, etc., has been prevented. And 4. That the foods will have keeping qualities that should be expected of the product. Finally, The numbers and kinds of organisms in most foods decrease during storage in the dry or frozen condition. If an average standard is adopted, half of the food samples are eliminated. If legal action is involved, the level of a standard must be justified. Counts or results on a sample by prosecutor, defendant, and Q-neutral agency may not necessarily agree. The National Academy of Sciences, Food Protection Committee, has suggested the following definitions of microbiological criteria for food safely. A microbiological specification is the maximum acceptable number of microorganisms or of specific types of microorganisms, as determined by prescribed methods, in a food being purchased by a firm or agency for its own use. B. A microbiological standard is that part of a law or administrative regulation designating the maximum acceptable number of microorganisms or of specific types of microorganisms, as determined by prescribed methods, in a food produced, packed, or stored, or imparted into the area of jurisdiction of an enforcement agency. An additional definition was suggested by Elliott, 1970. C. A microbiological guideline is that level of bacteria in a final product, or in a shipped product that requires identity and correction of causative factors in current and futures production, or in handling after production. An excellent text dealing with the philosophy, establishment, and implementation of microbiology criteria is the report by the National Academy of Science, Food Protection Committee, 1985. It has been recommended that 1. Testing procedure and standards be adapted to the particular kind of food. 2. A numerical relationship be demonstrated between the standard and the hazard. 3. Tolerances he allowed for admitted inaccuracies of sampling and analysis, i.e., ill samples would not be required meet the standard and results from successive samples, taken at staged intervals, would be considered in selling and interpreting standards. And 4. Any suggested criteria be tried out first on a voluntary basis. An increasing awareness among consumers, the demand to be informed, and confusion over the significance of a high number of bacteria have provided consumer pressure for adoption of bacterial criteria for some foods. Conversely, a general inability to correlate cell numbers or indicators with a possible health hazard and the seemingly low risks to consumer from many food products appear to lead to hesitation toward adopting standards for these food items.